Assalamu alaikum, doctor. How are you? My name is Saif Ahmed, and in this presentation, I will discuss the Power Distribution Lab 2, which talks about voltage regulation and capacitor placement using the IEEE 33 bus radial distribution feeder. So the simulation was completed using Python and Panda Power to study the voltage and feeder losses, also the reactive power and the power factor. So as you can see here, I did the code, and first, I simulated the feeder without capacitor compensation. The minimum voltage was, as you can see, 0.91309 per unit, and the weakest bus was bus 17, since the voltage below is below the acceptable lower limit of the 0.95 per unit. The feeder has an under voltage problem. So the total feeder real power losses were approximately 202.67 kilowatts. And the substation supplied approximately 2.4435 mVAR of reactive power, and the substation power factor was 0.849. So the base case voltage profile confirms that several buses operate below the 0.95 per unit limit. Therefore, the feeder requires reactive power and voltage support. So next will be next, I installed a 0.3 mVAR capacitor at bus 17, which was the weakest bus in the original feeder. After adding the capacitor, the minimum voltage increased to approximately 0.91922 per unit. The weakest bus changed from 17 to bus 32, and the losses decreased to approximately 186.76 kilowatts, and the power factor improved to approximately 0.874. And here is the graph that compares voltage profile before and after capacitor installation. The compensated voltage profile is higher across the feeder, particularly at the downstream buses. So the capacitor reduced the losses by approximately 15.908 kilowatts, corresponding to a reduction of about 7.85%. However, the minimum voltage remained below 0.95 per unit, so the capacitor improved the system but did not completely eliminate the under voltage problem. So then I tested the capacitor size from 0.1 to 0.6 at bus 17. As the capacitor size increased, the minimum voltage and substation power factor generally improved. So this graph shows that the minimum voltage increased as the capacitor size increased. However, none of the tested sizes raised the voltage to 0.95 per unit. And this graph shows the relationship between capacitor size and feeder losses. The losses reached their minimum value of approximately 182 kilowatts with a 0.5 mVAR capacitor. At 0.6 mVAR, the losses increased slightly to approximately 182.72 kilowatts. Therefore, 0.5 mVAR was the best tested size for loss reduction. So the power factor, in this graph, the power factor continued to improve with the capacitor size and reached approximately 0.9 with the 0.6 mVAR capacitor. Next, I kept the capacitor size fixed at 0.3 mVAR and tested it at buses 5, 10, 17, 25, and 32. Bus 10 produced the highest minimum voltage, while bus 32 produced the lowest feeder losses. So the minimum voltage graph shows the bus was 10, that bus 10 was the best tested location for voltage improvement, with a minimum voltage of approximately 0.9192 per unit. So the losses graph shows that bus 32 gave the lowest losses, approximately 180 kilowatts. Therefore, the best location for improving voltage was different from the best location for minimizing losses. So then I performed an automated combined search using 6 capacitor size and 5 locations, giving a total of 30 configurations. So none of the 30 configurations satisfies the minimum voltage requirement of the 0.95 per unit. The highest minimum voltage was approximately 0.92189 per unit, obtained using a 0.6 amp capacitor at bus 10. The lowest losses were obtained using a 0.6 amp capacitor at bus 32. This confirms that the best voltage solution did not match the best loss solution. So, so next will be. I also tested the selected 0.3 amp capacitor at loading levels of 50, 50, 75, 0.5, 70, 0.751, and 1.25. These all are percentages. And at 50% loading, the minimum voltage was approximately 0.96252 per unit. The maximum voltage remained at 1 per unit at every tested loading level. So this graph confirms that no light load over voltage occurred. However, under voltage remained at loading levels of 75% and above. So here I compared one 0.3 amp capacitor at bus 17 with two smaller 0.15 amp capacitors at buses 17 and 32. And the split configuration increases the minimum voltage from 0.91922 to 0.92258 per unit. I also reduced the losses from 186 to 181.734. Therefore, distributing the same total capacitor capacity across the two buses provided better voltage and loss performance. So here, finally, I increased all feeder loads to 150%. Without compensation, the minimum voltage decreased to approximately 0.86344 per unit at bus 17, which is a severe undervoltage violation. And here I tested 55 single capacitor configurations using capacitor sizes from 0.1 to 2 mVar at buses 5, 10, 15, 5, 10, 17, 25, and 32. None of the 55 configurations satisfied the 0.95 per unit minimum voltage requirement. So the best configuration was as a 2 mVar capacitor at bus 10. It increased the minimum voltage to approximately 0.88668 per unit, reduced losses to approximately 417.1 kilowatts, and improved substation power factor to approximately 0.948. Although the capacitor improved the minimum voltage from 0.8634 to 0.88668 per unit, the results was still below 0.95 per unit. Therefore, one shunt capacitor was insufficient under the 150% peak load condition. So based on the normal loading results, switched 0.3 mVar capacitor at bus 17 can be used as an initial practical improvement. It improves voltage, reduces the feeder losses by approximately 7.85%. It also improves the power factor and did not cause overvoltage during the tested light load condition. So distributed capacitors produced better overload performance, while peak loading requires additional solutions such as multiple capacitor banks or voltage regulations or tap charging transformers or feeder reinforcements. So finally, a capacitor size and location must be selected by balancing voltage improvement, loss reduction, power factor, and changing feeder loading. So that's it for the presentation, and thank you.